Alright, we're going to try to do problems number 7 through 13 from your Physics C Mechanics practice test number 2. See if we can get those all into one video. Number 7, we've got a ball, a sphere of mass m, radius r, and rotational inertia I. So it's not, we know that a sphere is supposed to be, what's a sphere? Is it 2/5 mr squared? Well, they're actually just telling us to use I here, so we don't need to know that. It's released from rest at the top of an inclined plane of height h as shown below. If it's frictionless, well, if it's frictionless, it's not going to roll, so the moment of inertia doesn't matter. If it's frictionless, it could be a ball, it could be a puck, it could be a book, it doesn't matter what it is. It's just going to slide down. It's not going to roll if there's no friction. So that would mean that the energy considerations are pretty simple. It means that its potential energy, mgh, equal to its kinetic energy at the bottom. So that would give v squared is equal to, multiplying 2 over to here, v equals the square root of 2gh. And if you realize that frictionless means the moment of inertia is not going to be involved, then that automatically eliminates all 4 of those answers. Number 8, if the plane has friction so that it rolls, then we have a similar equation, but the energy, the potential energy, is going to turn into translational kinetic energy and rotational kinetic energy. And that's 1/2 I omega squared. Right? That's the translational, that's the rotational. And now we need to solve this for final velocity. So let's see if we can do that. mgh equals 1/2. Actually, let's multiply the whole thing through by 2, get rid of the fractions. mv squared plus, that's not in any of these, so we need to get rid of this. That's the same as v over r. So that's I times v over r squared, and you need to factor the v squared out of that. 2 mgh is equal to v squared times m plus I over r squared, and then divide that over to here. So v squared is equal to 2 mgh over m plus I over r squared. And if you multiply the top and bottom of that equation by r squared, you get E. I think it's pretty clear to see that it is that more complicated expression there we're going to get. Number 9. An object weighing 300 newtons is suspended by means of 2 cords as shown above. Tension in the horizontal cord. So let's see. We've got this tension right here would be 300 newtons. And this tension here, I don't know about that, but it would have 2 components, right? It would have this horizontal and vertical component, and then this one would have this component here. Well, the vertical component of this, since this is in equilibrium, this vertical component must match this vertical component. So if this one is 300 newtons down, then this component must be 300 newtons up. And that means, since it's a 45-degree angle, that would be an isosceles right triangle. Those 2 legs would be equal. So that would also be 300 newtons, because those 2 sides are equal in a 45, 45, 90 triangle. If it was a different angle, you could do some trig to find that. And if that horizontal one is 300 newtons, well then this horizontal one has to balance it out, since it's in static equilibrium. So the horizontal tension of that cord must be 300 newtons. Number 10. or 10, 11, and 12 all refer to these figures here. And you can see E right now. I'll slide that up in a second. So number 10, which figure best represents the free body diagram? When they say free body diagram, they do not want components of anything. They just want the forces. So this is no good. That has components. They don't want that in a free body diagram. If it's accelerating up the ramp, there's got to be a net force up the ramp. Here, you've got net force down the ramp. Here you've got, well, this is all weird. That's got a normal force that's not perpendicular to the surface, so that's not anything. That has a net frictional force up the ramp. And I don't think that just a frictional force on its own, friction opposes the direction of motion, so you can't have friction in the direction you're moving. So that can't be right. Here you've got a pulling force that's bigger than friction. That would be a net force in this direction. So that would be accelerating up the ramp. So it's got to be E. Number 11, we want the box if it's at rest on the ramp. Let's see. If the frictional force is downward, that's opposing the direction of motion. And, oh, there's another weird thing about this one, isn't there? Gravity is going in the wrong direction here, so we don't need to discuss that anymore. Well, I think that if it's at rest, there's no pulling force. Well, there could be a pulling force, I suppose, if there's static friction. But let's examine both of these. We know that this one has a bigger force, so this one was not at rest. Could this be at rest on the ramp? Well, static friction would oppose the direction that it wanted to go down the ramp, and if I think this could be exactly that. Gravity pulling down, there would be a component of gravity balancing this out, right? And then the normal force there, static friction would keep it in place. So that looks good for at rest. And then what if it's sliding down the ramp at a constant speed? Well, remember, at rest is net force 0, and constant speed is net force 0. So that would look just like this, in fact. So that's also figure C. Remember that A, B, and D, for one reason or another, can all be eliminated. This one because gravity is going the wrong way, normal force is going the wrong way in B, and in D they have components in there. It's not supposed to be in a free body diagram. So C and E are really the only choices allowed. All right, 13. Momentum is given as P equals KT cubed, where K is a constant. The force is given by what expression? Well, let's see. Looking at these, don't you think they want us to either take the derivative of this or the antiderivative? And they're both there. So let's get rid of everything else. The derivative of this is that, and the antiderivative is this. So I'm leaning immediately toward one of those two. Now let's figure out which one it is. Momentum, so let's see, change in momentum with respect to time is equal to impulse, right? Which is the integral of force dt. So if you wanted to get force from this, I could take the derivative of both sides of this equation and get dp dt is equal to the derivative of this. Fundamental theorem of calculus, derivative and the integral cancel each other out. So the derivative of momentum is force. And so the derivative of this, that's A. This is actually how Isaac Newton understood or formulated his second law. He thought about it like the change in moment, the derivative of momentum is equal to force. How is this equal to, well, let's think about what momentum is. Momentum is mass times velocity, so, and mass is a constant, right? So that'd be like mass times dv dt is equal to force, and dv dt is A, right? So that's just a version of Newton's second law.